Welcome back. In this video series, we are now going to take a look at how to calculate eigenvalues and eigenvectors. So in our previous video segments, we proposed the following. We said that every square n by n matrix has n eigenvalues and n corresponding eigenvectors. So if it's a 2 by 2, we expect to have 2 eigenvalues and 2 corresponding eigenvectors. It has to be a square matrix. It does not apply for non-square matrices. And lambda is called the eigenvalue of A corresponding to eigenvector V. And we referred to this equation here as the Eigen Equation. So we can call this the Eigen Equation so that we can always reference this guy as needed. And what the key geometric interpretation was is that if I take a vector, and it is in fact an eigenvector, and I multiply it by A, that is, I perform a transformation, which we know in general, a matrix, when it multiplies a vector, could take that vector and rotate it and maybe stretch it as well. Maybe that vector becomes, this vector here becomes this vector here. But the special thing about eigenvectors in particular is that the transformation that takes place is one that only ends up scaling the vector itself. And any vector that satisfies this equation is called an eigenvector. So here's a picture of the matrix 2, 4, 4, 2, and 1, 1 turns out to be an eigenvector of this matrix. So when multiplied by A, if it is an eigenvector, it gets scaled only. No rotation takes place. And so if we look at the 1, 1 vector, and we multiply it by the A matrix 2, 4, 4, 2, we get the vector 6, 6, which means that the 1, 1 vector was scaled by a factor of 6, and therefore we can say that the eigenvalue here, the eigenvalue is lambda equals 6. And once again, we can write this as 6 times the 1, 1 vector. So all that happened to the 1, 1 vector down here is it got scaled up by a factor of 6. So the applications of eigenvalues and eigenvectors are extensive and used in data science, mathematical modeling. They're used all over the place. We'll address them soon. We've already seen them in the context of steady states. There's some really powerful things that emerge from this. And anytime you're multiplying a vector by a matrix, you want to be thinking about eigenvectors. So last time we were able to calculate how to find eigenvalues given an eigenvector and vice versa. But where does the hunt begin if you have neither the eigenvalue nor the eigenvector? So we have to go back to the Eigen Equation. This is the thing that we need to focus on when we're going to be finding eigenvalues and eigenvectors. So with the Eigen Equation, if I do a little bit of algebra on this, I can rewrite this as AV minus lambda V equals the 0 vector, so subtracting lambda V from both sides. And this might look familiar. This is a step that we did whenever we already had the lambdas and we were looking for the vector. So the next thing we did is we wrote the identity matrix in here, and we packed the identity matrix right in between the lambda and the V. And the reason we did that is because if I factor out a V, I simply cannot have A minus lambda in parentheses because A is a n by n matrix, lambda is a scalar. So by putting an n by n identity there, now the algebra works out. It seems like a very weird thing to do that you'd have to introduce that in there, but A minus lambda is simply not defined. So we factored a V out, and now we want to reason through this a little bit. So this will always have the solution V equals 0, 0. It is always a solution to this. Why is that the case? Well, if we think about this as just being some matrix, right? This is just a matrix full of values in here. And let's just refer to that for now as C. And so if we write our equation as C times V equals 0, and we think about what is inside of C. Well, if C is a 2 by 2, for example, then we would have some values inside of this matrix. And the eigenvector just has some x and y component equals well, let's actually suppose that v consists of the 0, 0 vector. So if this in fact had both components equal to 0, well then we take 0 times the first column plus 0 times the second column, and what we can see is that we get the 0, 0 vector. So this will always have this trivial solution, and if that's the case, then every time we solve this equation, we're only going to end up with the eigenvector is the 0, 0 vector. And it's true because when you multiply the 0, 0 vector by anything, it still remains the 0, 0 vector. So you could say that the 0, 0 vector got scaled and still remained as the 0, 0 vector. So one of the things that we can observe is that, so we said that the equation a minus lambda I times v equals 0 can be thought of as c times v equals 0, where c takes on the a minus lambda I. The only reason we do that is just so that you can see that the coefficient in front of v is just a coefficient matrix. Now, we said that 0, 0 is going to be one of the solutions automatically, and here's, again, that justification typed out. So how do we get more than just the 0, 0 vector as a solution to this? Well, keep in mind that we still haven't found lambda, that lambda is an undetermined value. Now, in general, we can force, since c depends, since that coefficient matrix, c depends on the value of lambda, we can force this equation to have infinitely many solutions. Again, since it's already the case that v equals 0 is a solution, but we want a non-trivial solution. So trivial solution is the solution 0, is the 0 vector. We do this by requiring the determinant of c, which is a minus lambda I, that be equal to 0. So in other words, that is, find the lambda values by solving the determinant of a minus lambda I set equal to 0, solve for lambda, and then once we have the lambdas, we already know how to compute the eigenvectors from that. So let's go ahead and implement this so that we can see how this works. So here's our previous matrix, which we've already found the eigenvalues. We were given them as, I believe, positive 6 and negative 2, but how would we go about finding its eigenvectors? So once again, we always need to step back to the Eigen Equation, which is AV equals lambda v, because any eigenvector is a vector satisfying this equation. And we rearranged this. We wrote this equation already as a minus lambda I times v is equal to the 0 vector. And what we need to find is we need to find what should lambda be so that the determinant of a minus lambda I is equal to 0. To find that value, what we want to do is, first off, compute a minus lambda I. So if I compute a minus lambda I will have the matrix 2, 4, 4, 2 minus some unknown scalar lambda multiplied by the identity, which will just be lambda, 0, 0, lambda. So the identity, remember, has the components 1, 0, 0, 1 in it. And when you scale that matrix by lambda, you get lambda 0, 0, lambda. When you subtract these, you get 2 minus lambda, 4 minus 0, 4 minus 0, and once again, 2 minus lambda. So we want the determinant of this thing to equal 0. So to calculate its determinant, we now are going to take the determinant of the 2 minus lambda, 4, 4, and 2 minus lambda. And so to find determinants, we know that that's these components multiplied together, subtracted, and then we subtract away these components multiplied together. And so we will have, and I'm going to continue writing that down here, but here we'll have 2 minus lambda times 2 minus lambda minus 4 times 4. And so if we do a little bit of distributive property on this, and we set it equal to 0, so notice that we're going to set this equal to 0. We're going to have, if you FOIL this out, let's see, we'll have lambda squared. and then we'll have a minus 2 lambda, another minus 2 lambda, so that will give us minus 4 lambda. And then we'll also have 2 times 2, which is 4, and then minus 16. And that comes out to lambda squared minus 4 lambda minus 12 equals 0. Now that's a quadratic function, and lambda is just a variable at this point. So to find lambda, I could try to use quadratic formula. I could use the method of factoring. In this case, it will work to factor it, but you could also just use quadratic formula. I'll show you a faster way to do this as well. So negative b, so negative 4 plus or minus, this is lambda equals the square root of negative 4 squared minus 4a times negative 12 all over 2a, and the a value is 1, so this is just over 2. And this comes out to, let's see, 4 plus or minus 16. This will be plus 48, which will be 64. So the square root of 64 all over 2, which comes out to negative 4 plus or minus 8 over 2. And so this gives us 2 lambdas. Call them lambda 1 and lambda 2. Which one's which, it doesn't really matter. So negative 4 plus 8 is 4 over 2 is, let's see, my mistake, that's going to be 12. Positive 4 plus 8 is 12 over 2 is 6. And lambda 2, 4 minus 8 is negative 4 over 2 is negative 2. And you can see that these were the same ones we were given in our previous video series. So now that we have the lambdas, the next step is to solve for the eigenvectors. And so we're going to have to do this twice. So we're going to look for v1, which is going to be based on knowing that lambda 1 is 6. So we want to know what is v1. And then over here we'll do v2. We'll find that, and we know that lambda 2 is negative 2. So now we have to plug this back into the Eigen equation. So recall that a minus lambda I v equals 0 is our Eigen equation. And if I take, so now I know what a minus lambda I is already. A minus lambda I is the 2 minus lambda 4, 2 minus lambda matrix. But I already know what lambda is. So I'm going to write this out in scalar form so we can see what it is that we're after. We're after the x and y components here. For lambda equals 6, if I plug in 6 for lambda here, then we'll have a minus 6 here, and we'll have a minus 6 here, and that's just based on our lambda value. And now I actually have a coefficient matrix, which you can see is going to be negative 4, 4, 4, negative 4, and this should look very familiar. This is something we did in our previous video series on introducing eigenvalues and eigenvectors. And now we can solve this system, and we should end up with infinitely many solutions. So negative 4, 4, 4, negative 4, and then augment that with the 0, 0. Perform Gaussian elimination, and what we're going to end up here with is 1, negative 1, 0, 0, 0, 0. So we see that this converts into x minus y equals 0 and 0 equals 0, which is a true statement. Now, because there's no statement telling us what y has to be, we can say that y is a free variable. So y is a free variable. And so we can say let y be some constant, and that means x, y, our eigenvector, or it's the components of that eigenvector are going to be, well, y is c, and then x is going to equal c as well, because x minus y has to equal 0, so this implies x equals y. And so any solution where x and y are both the same value will work. And then this is the point where you can choose whatever vector you want other than the 0 vector. If you choose c equals 1, that's a nice choice because that will give us the 1, 1 vector, and that's our eigenvector from the previous example. In the next video, we'll go ahead and compute the eigenvector for the second eigenvalue. See you there.